Okay. Dear colleagues, good morning. My name is Daniel Gulaev, and first of all, I need to check the sound. So please give me a hint. Can you hear me? Is everything okay? Okay, very good. So my name is Daniel Gulaev, and I am presenting as an employee of Sofoil company. First of all, I must thank NAFTA College for providing this platform for presentation. For about almost 20 years, I was an employee of a producing company, but now I'm for more than 5 years an employee of service company Sofoil, and I think that it could be very interesting for you to find out what can we see from the regular production data and what information could be got from there for better understanding your reservoir and improve your production without any additional implementations, only on base of historical data. So we call this service Multiwell Retrospective Testing, and I will be happy to show you this opportunity. And you can ask the questions at the chat. And I will temporarily look there, and I can answer all your questions during the presentation. So, what issues could be solved by this MRT service? Suppose you have a production decline in the area, despite you have a pressure maintenance system, but still your liquid production decreases. We can reveal the reason of it and provide some recommendations for production increase. Other issue is water breakthrough. If you have several possible sources of water breakthrough, and it's not clear which of them reduce your oil production, we can reveal it. And if you have production decline more than expected in some wells, we can focus on that wells and also understood what is going on. And concerns, if you are not sure in the reservoir volumes, we can clarify what are the drained reservoir volumes, or what is the reason of formation pressure decline. Or if you have several faults partially sealing and you are not sure are they completely sealing or not, so we can reveal what is the reservoir compartmentalization. And if in general you have an area of the field or the whole field with unclear potential for production enhancement, we can clarify this. So what is it? Let me show you on the one of the case studies. For example, this was a relatively big field and there was a problem area. There was a well number 18 with water cut increase and oil production decrease. and there was not 100% clear which of the wells of injectors affects our production and damage it. Maybe I should explain. This is the aerial map. These points are wells. These bubbles are production or injection. If it's blue, it is a current injection rate. If it's green or brown, it's current production rate. And green is water production, brown is oil production. So we've decided to do this MRT on these 5 wells to see how the wells affect around the well 18 affects it. How do they interfere? The important point that well 18 had permanent downhole gauge. Because to reveal this interference, we need not only production data, but also bottom hole pressure data. Okay. And the goal of the test was identification of water source, water breakthrough. After we will reveal the reason of water cut increase, we can reduce oil production decline on that area. So to achieve these goals, we must fit the following objectives. First of all, by MRT, we will reconstruct formation pressure history for the pressure tested well, the well at the center of the test, number 18. And we will reconstruct productivity index history to see does it have a constant productivity or it can increase or decrease due to skin factor changes versus time. Then we will estimate skin factor, reservoir transmissibility, from which we can calculate permeability, and we will evaluate the drainage area of the pressure tested well, number 18. Maybe the most interesting, we will reconstruct the history of cross-well interference. And we will be able to evaluate reservoir transmissibility between the wells, between our pressure tested wells and each of the offset wells. And we can reveal the wells with the suspects of cross flows. So how can we do it? We do it by doing multi-well retrospective test, and it is a service to meet these objectives by analyzing rate history and pressure history with multi-well deconvolution technology. It's a mathematical algorithm to evaluate independently pressure changes caused by the rate changes of every offset wells in pressure tested well. Let me demonstrate it. This is the production history of these wells. First production was number 13, and then 20. First it was a producer. After that it was converted to an injector, and injection rate was much higher than the production rate. And the same was with well 21, but it happens much later. There was a short period of production and a period of injection. And during all the production history of well 18, we had a bottom hole pressure history measured by permanent downhole gauge pressure gauge, and rate history. And the blue line is water cut history. So what does multi-well deconvolution does? It looks at the pressure change during the production history and connects these pressure changes with the rate changes of well itself and rate changes of each of the offset wells. So if there were a lot of rate changes and none of the rate changes correlates with the bottom hole pressure changes, then we can conclude that there is no connection between those wells. But if there were a lot of rate changes and each of them corresponds with the small pressure changes in our pressure tested well, we can calculate the pressure transient response. Pressure transient response is the pressure changes in our pressure tested well due to unit rate production. Unit rate production of the well itself and unit rate production of each of the offset wells. Okay, so and what can we do with that? If we have this unit rate pressure response, we can convolve the actual, we can mathematically stop our well in past and reconstruct formation pressure. We can choose for how many hours should we stop our wells. Usually we take the number which is at the end of radial flow, about 500 hours, something like that. So we can do it several times, and then we can, by doing this, we can reconstruct formation pressure history. So we can see that for that well, here in this case, production formation pressure was changed really high. First there was a high decline of formation pressure, and then it was formation pressure increase. After that, when we have calculated formation pressure and we have rate and bottom hole pressure, we can calculate productivity index history. Here it's with red dots. And we can see that in the first and second period of production it was more or less constant, but at the third period it was decreased. And here between first and second period there was a short build-up, this one. So we were able to compare what was the reservoir pressure from that build-up interpretation and what was the reservoir pressure which we have reconstructed. And it was almost the same, actually, at 1650 psi. So our reconstruction was good. And here productivity index were decreased because of well killing. Why? Here we have decided to increase production and change the pump. It was electrical submersible pump. Yeah. So to change the pump, the well was killed, and despite the rate was increased because drawdown was increased, but productivity index was slightly decreased. So if we were able to evaluate pressure transit responses, we would be able to see in what periods of time there is a mismatch between rate changes and pressure changes. And in this period, we can correct the rate. So if we 100% sure that total production is correct, and we can demonstrate the periods where the rate measurements was not pretty good. Okay, and maybe the most interesting is interference plot. We call it a spider plot. What is it? On x-axis it's time, and on y-axis it's pressure impact. So we can see what was happening with time. When the well 20 was in production, the rate was very small, and production of well 20 has almost no effect on pressure in the drainage area of well 18. But when we start to inject quite a lot of water, now pressure here start to increase, and this slope of increase corresponds to injection rates. Here it was bigger rates, then smaller, then bigger again. So the bigger the rates, the bigger the impact of this well to the pressure of that well. And then at the end we decrease the injection rate, so impacts start to decreasing. And the total pressure impact of injection of well 20 on pressure at well 18 is 363 pounds per square inch. And during the last month of injection, it was 20 psi increase of pressure here due to injection of well 20. Okay, then well 13, if we consider producer, then it doesn't increase the pressure, it decreases the pressure. Despite it was the first producer, its impact is not too big. We have the impact of this certain well history here. It's about 100 psi during the whole period of production. But the well 15 impacts much higher. It's 230 psi only for the last month, and the total impact during the whole production history is 1300 psi. And the well 21, despite its start to inject much later than when well 20, and despite it's farther from the well 18 than the well 20, its pressure impact is much higher. It's twice higher than the well 20. So without that information, by only looking at the plot, I would suspect that the reason of high water cut in well 80 is well 20, because it's inject a lot of water and it's closer to well 18 than this one. But in fact, after we have done this analysis, we can see that the reason of water cut increase in this well is well 421 because its pressure impact is much higher. So we can reduce the injection in that well to reduce the water cut here in the well 18 and produce more oil. And one more thing that we can get from our technology is transient responses interpretation. What is pressure transient response? It's the pressure changes due to the production of the well with the rate of 1 barrel per day. And it lasts as long as we have the pressure and rate data. So we can see much farther than any pressure transient analysis data. And we can interpret it with traditional technologies of pressure transient analysis, but it will give us much more information about the reservoir. At the first part, it would be the same as the pressure transient analysis. We would see, so we use the technology of pressure transient analysis. So here we present the pressure and pressure logarithmic derivative in the dual logarithmic scale, logarithm of time and logarithm of pressure and pressure derivative. So after the well-bore storage, we would see a radial flow, and from that we could get reservoir transmissibility in the drainage area of the well. And then we can see the boundaries. So here it was not the geological boundaries, it was the effect of all the wells which were much farther from our pressure tested well than this one. There were some injectors and producers, but producers were more than injectors, so the total impact is looks like no flow boundaries. And from that we can see the whole drainage volume of our pressure tested well with the nearby wells. Comparing to the traditional rate transient analysis, it would be bigger, because if we do rate transient analysis, we could see only the volume of formation which were drained by this well itself, and these two wells would be like no flow boundaries here, and this would be like constant pressure boundaries here. But when we do MRT, we reveal these transient responses of any of offset wells, and we can see the pressure response of the production, which is from which we eliminate the influence of the nearby wells, so we can increase the area of scanning. Okay, and so this was the drawdown transient response of the well 18, and each of the offset wells, for each of them we can see the cross well transient responses, which we can interpret like an interference test, and also get the reservoir transmissibility from that test. So we have pointed here the reservoir transmissibility of the connected part of the formation between those wells, and here it's more or less the same, 200, 150 and 260, but here it's 700 100. So we have plotted here. It's much higher than our expectations from the open hole logs. And because of these two factors, one is our pressure impact of that well is not as high as it's supposed to be. And the second is that our transmissibility is unrealistically high. We can assume that this well may lose some of the injected water. It could be a cross flow in that well, because if we mathematically assume that all the water is going into our target formation, then we would increase our reservoir transmissibility. Okay, so our recommendation here was to do production logging with temperature gauge to see is there any cross flow, because other explanation could be that most of the injected water is going not toward to our pressure tested well. And to clarify this, we can do production logging. Okay, so that was the first case with an explanation of what is MRT, Multiwell Retrospective Test. I think now I should look at the questions and before going to another case. Okay. In page 6, how did you reconstruct formation pressure? Okay. Yes, I think I should explain one more time more specific. First of all, by looking at the pressure changes here, we have evaluated what would be the pressure response on the unit rate production. This response is drawdown transient response of the well itself and cross well transient responses of each of the offset wells. And now if we have that function, it's just a mathematical function of pressure changes due to rate, we can calculate what would be pressure in our pressure tested well if we would stop it for any period of time. So we have mathematically stopped our well here and looked how was it pressurized for 500 hours and got that pressure point. Then we stop our pressure here and got that pressure point. Then here and here and here, and we mathematically stopped our wells with the constant period of time by the same period of time. And we have got the line with our pressures, how it was changed with time. And here there was no injection, so our pressure rises not very much. But here, when we have a lot of injection, because our well 18 was mathematically stopped, but injection was still ongoing, our pressure rises much higher from bottom hole pressures than here. And also rate here was bigger because drawdown was bigger. So we also get the bigger values. Okay. What do you mean by deconvolution? Deconvolution is a mathematical procedure of analyzing the rate changes and bottom hole pressure changes, and we are mathematically changing the pressure transient responses to be able to match the actual bottom hole pressure with the reconstructed bottom hole pressure. And the reconstructed bottom hole pressure is calculated by the actual rates of the well itself and all the nearby wells by changing the transient responses. So we reconstruct it and if we see the best match, we can say that this is a solution. From that we could get these transient responses, which we use to get all the other MRT results. Are you using specific software or just Excel? No, deconvolution cannot be done in Excel. So we do use our internal software. We call it Polygon. But for now it's only internal, but in the near future we are going to provide it as a market software, so anybody could buy it and use it for this kind of tests. And it also can be used for any pressure transient analysis or rate transient analysis. Is the spider plot from well 18 observation effects or how it was plotted? When we got these transient responses, we just convolve this pressure transient responses with an actual production history and injection history. So that from that we could get this interference history. Can you explain more detail about negative pressure impact? When we produce, we decrease the pressure. So each of the production wells decreases pressure in our well also. Of course, the biggest pressure impact would be from the well itself, but with time, other wells also start to decrease pressure in our pressure tested well. That's why we have a negative pressure impact from the producers and positive pressure impact from the injectors, because when we inject water, our pressure increases. Okay, so let me show you, that would be for one reservoir. Let me show you another case, which was published in SPE paper here. It's interesting because it has several layers. Because usually people say, okay, we can this technology works fine for one reservoir, but what can we do with if we have several reservoirs? Okay, what was the problem? The well 37, it has a bottom hole pressure gauge, and we had a very long production history in that well, and it had a problem. It had a production decline for about 10 months. And we had 3 producers and actually 3 injectors here. two was injectors here and here, and this well had a dual stream completion, and from one of the formation it was produced, and into another formation it was injecting water. There was such three reservoirs. In some areas, some of the reservoirs layers was pinching out. Some of the layers, all the wells were there. So it was quite a complex case. This is the current rates, and this is cumulative rates, cumulative production and injection. And these layers, some of them were more or less contained, and other was splitting in the areas, and there was a not quite people were not 100% certain about the correlation of that intervals. So it was important also to understand does the well interfere or not. Okay, so we have taken about 4 years of production of the well 37. There were several build-ups due to technical reasons. So here it was not so difficult to reconstruct the formation pressure, but to reveal the well interference, it was challenging without MRT. Okay. So the goal was also to reveal why we have a production decrease at the last period of production, and to see what is the cross-well interference, and to recommend what should we change in our injection wells mode to increase production in well 37. And also to achieve that goal, we decided to reconstruct formation pressure history of the well 37, predict formation pressure, forecast formation pressure if all the wells would produce and inject with the current rates, reconstruct productivity index of the well 37, estimate current skin factor, transmissibility, and the drainage area. Actually, it's interference-free drainage area of the well 37. Reconstruct history of cross-well interference with each of the wells nearby, and estimate cross-well transmissibility of the connected part of the formation between our well 37 and each of the offset wells. So here is reconstructed formation pressure. Initial formation pressure was a little bit higher, but bubble point pressure is quite low, so there was no problem in formation pressure, well, not much problem up to this period. But after that, our formation pressure started decreasing. And actually, that is the reason why we have a rate decrease here. We have done the forecast at this period. If our well would produce with the same rate, and all nearby wells would produce with the same rate and inject, our forecast would be decrease in pressure. So if we do nothing in this area, this I hadn't said, this blue dots is the actual bottom hole pressure. Black dashed line is reconstructed bottom hole pressure by the multi-well deconvolution. Here in this period there was lack of data, so we have reconstructed it here. And here we have made a forecast of bottom hole pressure and reservoir pressure. So if we do nothing in this area and continue to produce as we do now, our formation pressure would decrease, and actually if we would have constant bottom hole pressure, our rate would decrease. So we need to change something definitely to increase our production. And this is productivity index. Here, through the whole period of production, it was more or less the same. There was no problem here with the productivity index, only with the reservoir pressure. And then we can see this black dashed lines is drawdown pressure transient response. We had pretty long pressure buildup here. It's blue points. And we have done a comparison of this pressure buildup with drawdown pressure transient response. And you can see that the pressure buildup is much shorter than the drawdown pressure transient response. So it could see much farther what is going on with the reservoir. And we can see the boundaries here, which cannot be seen from the pressure buildup. Actually, we can see rise here, the derivative with the pressure buildup, due to influence of nearby producers. But its influence was withdrawn from our drawdown pressure transient response. So we can see interference-free response. Okay, and it can be interpreted like pressure transient analysis. We can see the reservoir transmissibility. We can see the total skin factor. It's negative here because the well was stimulated by the fracturing, hydraulic fracturing, but it was quite a short fracture, only 10 meters. Then we, from transmissibility, assuming the all net paste is producing, we have calculated the current phase permeability, and we recalculated it to absolute permeability, and it's much less than open hole values. So maybe it could be something wrong with porosity permeability relationship, which was used in open hole log interpretation. Or maybe not all the production, not all thickness is into production. But here it's not the case because we had a production logging historically somewhere here, I suppose. So here all the net thickness were in production, and the problem was with the relationship, of course. Okay, so that's information we can got from pressure transient response. And then we have reconstructed the interference, cross-well interference. And what have we found? That this well 107 affects our well 37 not too much. It's only 20 kilopascal per the whole period, and during the last month it was 0.5. So yes, there is a connection between them, and injection of this well affects our pressure tested well, but not too much. Other two wells, this 45 and this 36, affects much higher. This 36 is affects by 40, and this 45 affects by almost 90. And the difference is due to injection history. First of all, they were more or less the same, and then the well 36 was stopped, and then injection was decreased significantly comparing to previous injection, and that's why its pressure impact decreased, and we have a less impact than it was before. And this well decrease is the main reason of formation pressure decrease here. So we have recommended to increase the injection into this well to avoid rate decline in our well and increase production. Okay, and we also interpreted cross-well transient responses to get the average transmissibility of the reservoir, apparent reservoir transmissibility of the connected part of the reservoir between those wells. It's 13, 20, and 36. And this is transmissibility. And again, it's much lower than open hole expectations. And it's partially due to permeability overestimation, about 2 times as we saw in the previous slide. But also it's much less because not all the reservoir thickness is involved in interference, because we have pinching out and we have not reservoir thickness, not all reservoir thickness interfering. It's not so good because of that we have water going from injector to a producer through only part of the formation, which increases water speed and increases water cut finally, and due to that we have lower recovery, because in some part of the reservoir there is an oil which is not sweeping by the water injection. So here I must maybe explain one more time about this drawdown transient responses. How do we calculate transmissibility and what also we can see? The left part is the theoretical part. If we have closed system and 2 wells here, one is producer and one more is producer, and we will do MRT in that case, then what we would see? We would see pressure transient response, which of our pressure tested well, from which we can get reservoir transmissibility and skin factor and the volume of the reservoir. And here, if we have the same transmissibility, if it's homogeneous, and if we have the same drainage volume, then the cross-well transient response by these gray dots will also demonstrate us the same reservoir transmissibility and same drainage volume. And what have we see here? We can see that reservoir transmissibility, cross-well reservoir transmissibility is lower than reservoir transmissibility of the part of the reservoir drained by the well 37. But the volume which is drained by the well 45 is bigger than volume is drained by well 37. And that's because of the complexity of the reservoir geology here. And that transient response, drawdown transient response and crosswell transient response, could be matched with numerical model. We call it XPM, crosswell pressure modeling. We can add several layers. We can add points of thickness, different porosities, and match the transient responses with the numerical assumptions of our geology. But that's a pretty complex, pretty long talk, so I will not spend a lot of time on that now. But I just want to say that it's possible, and from that we can reveal our geology maybe more in another way than the usual technologies. We can see what are the drainage volumes of each of the wells and see is there any potential with an undrained parts of the reservoir for now, for example. Okay, so what has happened after that? It was quite an old job. It was done in the 2018. So we have a history of results on our recommendation. When we recommended to increase the injection in that well, our pressure and rate has changed. Instead of declining, we have increase in our bottom hole pressure and reservoir pressure. And if they would increase the rate by decreasing the bottom hole pressure, if they would maintain the same bottom hole pressure, our rate would be increasing. So we can see the clear response. Instead of decline, we have an increase. And the water cut was the same, so there was no negative influence, only positive in terms of production potential. And to check the technology of MRT, the customer decided to do the pressure build-up here at the end of the test. So there was a blind test. Black dotted line was the reconstructed bottom hole pressure in the well 37 during production and during build-up. And the blue is an actual points. So we can see a pretty good match with the reconstructed pressure. And after that we had quite a lot of jobs with this customer. Okay, and I think important point is to demonstrate the difference of MRT and the traditional rate transient analysis. If we do rate transient analysis and the well is only in production without shut-ins, we could get the initial formation pressure. Well, we must take it from somewhere, and we can say how would the formation pressure change. But during this, we need to assume our productivity index constant. Or we can evaluate how was productivity index changed if we assume that formation pressure is constant. We cannot separate them without any additional well shut-ins. But with MRT, we don't need it. We would reconstruct formation pressure independently and productivity index independently. And from this productivity index, we can say the skin factor dynamics. We can find the periods where the skin factor was worse than it was before, and we can calculate what would be an additional production increase if we eliminate the skin factor. Okay. Then difference is in well drainage area. By rate transient analysis, we can evaluate the well drainage area, but with the dynamic boundaries. Each of the wells around our pressure tested well would affect that. And if we have several rate changes in production wells, we would have no flow boundaries. If we have several injectors, it would look like constant pressure boundaries. But by MRT, we eliminate this interference from our drawdown pressure transient response, and we will get interference-free drainage area, which we will have the same as formation transmissibility. From that we can calculate the reservoir permeability if we get the information about the thickness from which we have production. And in rate transient analysis, we could see no flow or constant pressure boundaries, and we cannot separate are they the geological boundaries or they are due to production and injection of other wells. But here in MRT, we can separate these boundaries. Geological boundaries we would see, and instead of just one boundary response here, we can see the quantity of interference history with each of the offset wells. And also, if we have an aquifer, we can also get this plot of history of aquifer support or gas cap support, because it would be a pressure increase which is not correspond to any injection changes of an injection well. So we can extract our injector support, and all the last support we have would be from the aquifer. And limitations. Each technology has its limitations. So first MRT limitation, that we must have a bottom hole pressure record. If we have a tubing pressure, if we have a pressure at the surface only, well bore effects will be much higher than the interference, so we will not be able to get this from the producers. But if it's water injection well, then we can recalculate its surface pressure to bottom hole pressure and use it for multi-well deconvolution. And offset wells may not have bottom hole pressure records. We need at least one well with a bottom hole pressure gauge to be able to reveal the pressure interference. Okay, that's the first obligation to be able to do MRT. The second one, that we should have historical production and injection data records, and they must be reliable. If there is some mistakes in production history, we can recalculate it, we can fix it. But if there is a lot of mistakes in our production and injection history, our MRT would be misleading. And we use the total bottom hole production. I haven't said that, but I should. We use the total history of each of the phase we produce. We recalculated it to bottom whole rate of the whole fluids we extract. So we need to know also properties of each fluid to be able to recalculate surface rate to bottom hole rates. And the third obligation that we must have a lot of well rate changes. Suppose we don't have rate changes in one of the offset wells. In that case, we will not be able to get this pressure transient response from that well. So to be able to separate the interference with different wells, we must have a lot of rate changes, and they must not be simultaneous. If two wells change the rates at the same time, and we have the response in our pressure tested well, we cannot separate it because they were simultaneous. And usually this third obligation results in the situation that we must have a long production period, well, at least a half of a year, to get enough of rate changes to be able to do multi-well deconvolution. And this final slide, it represents how can we get a lot of additional oil here from that. And that this slide was already presented on the previous webinar, so I will not go to the details, but I will say that we have done MRT for each of the producers, and despite the injection was the same as production, but the reservoir pressure was decreasing because of cross flow in injectors, and we had quite a big areas with very small pressure, and some of the injectors inject all our water right to the producer, so that was results in water cut increase. And one of the recommendations here was to do something and to increase the production in that well. We have found out that this well injects this relatively small injector is the source of water in this well, and we have found that two wells doesn't affect this well. So this well suffers from water from that well and from absence of interference with the injector and pressure decrease. So we recommended to convert this well to injector, and this is a production history of this well. So we have quite a big liquid and oil production decline, and now it was almost 80% of water cut. And when we convert this well to injector, our pressure here in oil saturated zone increased, and we have 4 times increase in our oil production and a significant decrease in water cut only by converting this well to injector. Okay, so thank you very much. Now I will answer your questions, and also you can write the questions in our NAFTA College forum. I will answer them also. And this webinar will be available in the library of webinars. So, okay. So basically majority of those cases has PDG. Yes, the majority of those cases has PDG. We can calculate it from wellhead pressure only if there is a single flow, no gas. So in injectors we can calculate wellhead pressures, but in producers we must have PDGs. In Russia, quite a lot of wells has PDG on ESP pumps. But it also could be the bottom hole pressure gauges in Southeast Asia. Quite a lot of wells has bottom hole PDGs. If we have no PDGs, then we can install our own pressure gauges, and we can change the rates of an offset wells by purpose, and we call this pulse code testing. So if there is no PDG, we can use another technology to reveal the interference. Is your reconstructed pressure a unique solution, or can many different combination of properties between different wells give you the same reconstructed pressure? Well, actually, I should split these questions into two questions. First of all, we do not, it's only pure mathematics. We do not use the reservoir properties, combination of reservoir properties to give, to find out the interference. We have just curves of our rates, total bottom hole pressure, total bottom hole rates, and bottom hole pressure. And only after that, after we have done this multi-well deconvolution and found these pressure responses, after that the next step would be add some physics and interpret. We can interpret them, these pressure transient responses, like drawdown test and interference test. And about the uniqueness of the solution, that's the answer is here. If we have quite a lot of well rate changes and each of them responds in our bottom hole pressure, then it would be a unique solution, because we will have the lots of interference. But if we have only few of them, then it would be not a unique solution. So the way to increase the uniqueness of the solution is to have a longer production history. For multi-zones well analysis, did we have to allocate the production for a particular zone? Okay. If, for example, in the case I've demonstrated here, we have not had the allocation to particular zone, so that interference which I got, I cannot say from which of those reservoirs it happens. This 107 well, it injects into first and third formation, and this interference is an interference from both of them. Maybe in one of them it's bigger and in another one it's slower, I don't know, without rate allocation. But anyway, I can say how much pressure change would I have in well 37 due to injection of this well. And it's on base of this information, I can still do recommendations of how must I change the rates of all the injectors to increase the pressure in my 37 well and to be able to increase production in it. But if I would have rate allocation per zone for injectors and for producer, I would be able to do MRT separately for each layer, and I would get the reservoir transmissibility of each of the layers. But even if we don't have rate allocation, we can see the pressure impact, and on base of this pressure impact we could recommend what would be the optimum rates of injectors to get the optimum production from the producer. Okay, so yes, in that case we have treated all the zones as a single unit, but if we would have a rate allocation we could separate them also. I'm not sure enough the college policy about the sharing the PowerPoint presentation, but the video of this presentation will be absolutely available for you. Okay, is it possible to share presentation? Okay, the same answer. I don't know, but the video will be also provided to you 100%. How sensitive are the results to accuracy of gore? Okay, that depends what is the value of gas in the total production. The bigger the influence of gas in total production, the more sensitive results we would get to the possible errors in gas measurements. So yes, we have MRT is pretty good technology. It doesn't require field operation. It doesn't result in production deferment for the test, but we must have bottom hole pressure history and rate history. Only these parameters must be present, and they are important. If we have not much gas and in the total production, then it's okay. We can correct the rate because one of the MRT results is rate allocation correction. But if we have, for example, half of production is from the gas, then we must have good measurements of core. Okay, how does comminglant injection and pressure situation complicate the understanding? Well, for example, this 45 well has injector into first and second layer, but I can say only the total impact of the injector. I cannot say from which of layer it comes most and from which of layer it comes less. Only 36 injector from this, I am 100% certain that it's from the third layer, because it injects only into one layer. And with the rate allocation, we can separate this interference, and we can separate this transmissibility into layers, because for now this two transmissibility is from connected parts of two formations, first and second, so I cannot separate it actually. But here it's only from the one formation, the third formation, because we have injection only into one well. Okay, so thank you very much. I've spoken even longer than I expected. If you have any other questions, please type them into NAFTA College forum and I will answer. Thank you very much. Oh, okay, we have one more question. Do we have to calculate drainage area before performing MRT analysis? No. We call it static and dynamic drainage area. Both of them are results of MRT. We can calculate the dynamic drainage area, which is limited by influence of other producers. And we can calculate the potential drainage area, which is limited only from the influence of other offset wells of the second row or the geological boundaries. And this interference-free drainage area is quite interesting to see the geological boundaries. Okay. So again, thank you very much for your time, and please feel free to ask your questions in the forum. And for now, I will have to finish this webinar. Thank you very much.